Hello everyone. So welcome to my second lecture of this unit that is focused on radiation. In our last lecture, we have learned about the thermal radiation, its properties as electromagnetic spectrum, and we have also seen some definitions, the basic definitions that should be used in our future lectures, in our future topics, right? We have also learned about what is blackbody, what is the blackbody radiation, and then finally we have also derived some expression for pressure that is exerted by radiation. Now, in this lecture, we will study some other laws related to radiation. Particularly, we will focus on Stefan-Boltzmann law, and we will understand the black body spectrum. And to explain that, there are several laws which try to explain this black body spectrum. So we will see one by one. So the objective of today's lecture is to understand mainly blackbody spectrum and their related laws, such as Wien's displacement law, such as Rayleigh Jeans law. Okay. So the outcome after attending today's lecture, the students will be able to learn about the Stefan-Boltzmann law. Second point is to you will get the knowledge of blackbody spectrum characteristic. The third point is you will learn about the classical laws to explain blackbody spectrum, including Wien's displacement law and Rayleigh Jeans law. And finally, you will understand the reason of failure of classical theory, because these laws could not completely explain blackbody spectrum characteristics. Okay. So we will understand why these are failed and what are the possibility for the future development. So to start with, here is the content of today's lecture, which will be covered to attain the objective of this lecture. The first topic will be Stefan-Boltzmann's law. The second one will be distribution of energy in blackbody spectrum. We will see the spectrum in terms of energy and intensity. Then there will be two laws which would discuss to explain this black body spectrum. The first law is Wien's displacement law. Second is Rayleigh Jeans law. And the final two topics will be related to the failure of classical theory. Classical theory means the Wien's theory, Rayleigh Jeans theory, or Stefan-Boltzmann law, whatever the laws which explained black body spectrum on the basis of classical theory. They are all failed. Failed means they could not explain whole black body spectrum. They could explain only a part of it, right? And finally, because of this failure, there was origin of new hypothesis that was proposed by Planck, and these were known as Planck's quantum postulates. So we will today learn about Planck's quantum postulates at the end of this lecture. Here is the list of reference books which you can consider to study these topics and to understand it more clearly if you want. So let us start with the Stefan-Boltzmann law. So first we will see what is the statement exactly, and then we will see what we can do with this statement. So the statement of Stefan-Boltzmann law, actually this was first stated by Stefan only, and the law states that the rate of emission of radiant energy by unit area of a perfectly black body is directly proportional to the fourth power of its absolute temperature. In mathematical terms, we can write E equals to sigma T to the power 4. Where sigma is termed as a constant and known as Stefan's constant. The T is absolute temperature, and the value of Stefan constant was calculated as 5.67 into 10 to the power minus 8 watt per meter square per Kelvin to the power 4. Right? Now the Stefan's law actually refers to the emission of heat radiation only. It does not tell about any net loss of heat by the body after exchanging with the surroundings. Remember the Parvos theory of heat of the exchange heat, right? Heat exchange. There it is saying that all the bodies exchange heat energy or radiation with its surrounding until it reaches to thermal equilibrium. So this Stephen's law refer to only the emission which is radiated from the body itself. It does not tell about the any heat exchange. But anyway, it can be extended to represent the net loss of heat and can be written as follows. The statement says, for example, we can consider that if a black body at temperature T is surrounded by another black body. This is first black body. The temperature of this is T. It is surrounded by another black body. The temperature of that is considered as T0. So the net rate of loss of heat energy per unit area of surface will be given by E is directly proportional to T to the power 4 minus T naught to the power 4. So T to the power 4, the black body temperature, and then surroundings black body temperature, that is T naught and to the power 4. That's the difference. And that can also be written as E equals to sigma T to the power 4 minus T naught to the power 4, where sigma is again a Stephen's constant, and this law is in accordance with the Parvos theory of heat exchange. That means the net loss of heat is the difference of heat radiated by hot body and that absorbed by it from the surroundings. So whatever it is radiated and whatever it is absorbed from the surrounding, the difference of that can be given as a net loss of heat energy, that is represented by E. Okay, so this is about Stefan-Boltzmann law. However, until now it is known as Stephen's law. What Boltzmann did, that Boltzmann has given the theoretical proof of Stephen's law on the basis of thermodynamics, the theory of thermodynamics, and that's why combinedly this law is termed as Stefan-Boltzmann law. So now in the next topic we will see how Boltzmann has theoretically proved this law. To prove this, let us consider that actually it's not consideration, it is the theory with associated with the black body radiation. We have already learned that the black body radiation exerts some pressure on the surface where it is falling down, right? So it is exerting the pressure very similar to gases. We have already derived one equation for the pressure that is exerted by any gas molecules. So we can do the same consideration for black body radiation because it also exerts pressure very similar to gases. So thermodynamic, if it is behaving similar to gases, the thermodynamical relations, they are also valid for the heat radiation. Now if we consider a small u is the energy density of radiation inside a uniform temperature enclosure, that is at temperature T. Now for example, we are considering, let us consider that P is the pressure and V is the volume of that enclosure. Now if we apply first law of thermodynamics, what we can write, delta Q equals to du plus P dV. Now if we consider Maxwell's second thermodynamical relation, what it is saying, del Q upon del V at constant temperature equals to T into del P upon del T at constant V, right? It was actually ds, del S upon del V at constant temperature equals to del P upon del T at constant volume. If we multiply this with T, it becomes T into del S, that is del Q, and that's why T is here in the multiplication of second thermodynamic relation. Okay, now if we put the value of del Q from the first law of thermodynamics, what it becomes? It becomes del U plus P del V upon del V at constant temperature, and that can be written equals to the same term as right hand side. So T into del P upon del T at constant volume. Now opening this bracket, what we get is del U upon del V at constant temperature plus P, del V will cancel out with del V, so plus P will be remaining equals to T into del P upon del T at constant volume. If we take P on the other side, the equation will be as del U upon del V at constant temperature equals to T into del P upon del T at constant volume minus P. Let us term it as equation number 2. Now, since V is the volume of the enclosure, so the total energy of radiation that is inside the enclosure can be written as capital U, the internal energy, equals to a small u, because it is energy density and we know the volume is V. So the total internal energy will be given by U into V. Let us consider it as equation number 3. And we already know the pressure of diffuse radiation is given by P equals to 1/3 of total energy density. So P equals to U by 3. Let us consider it as equation number 4. Now if we differentiate equation number 3 and equation number 4 with respect to volume and temperature respectively, what we get is del U upon del V at constant temperature equals to U, and del P upon del T at constant volume equals to 1/3 du upon dt, right? This will be two equations. Now if we put these two equations, you see these terms are written in equation number 2. If we recall our equation number 2, you can see del U upon del V here, del P upon del T here. So we can put the values of it in equation 2. We get U equals to T by 3 into du upon dt minus U upon 3. We can take this U by 3 on the other side and it will become 4U upon 3 equals to T by 3 du upon dt. If we solve this, 3 will cancel out with 3. We will get du upon U equals to 4 into dt upon T. Now if we integrate this term, what we get is log U equals to 4 log T plus constant, and log U will be 4 log T plus constant, right? That is the simply integration of this. So log U equals to 4 log T plus, we can write constant as log into A. We can place any constant here. So we are placing this like this. Log U equals to log into A T to the power 4. This is our final term. Now if we remove this log from the both sides, it will become U equals to A T to the power 4, or since A is the constant, we can write this as U is proportional to T to the power 4, right? Now we also know that the total rate of emission per unit area of a black body is proportional to the energy density. That is, E is proportional to U, and that is proportional to T to the power 4. That is Stefan's law. So that's why we can say that E equals to sigma T to the power 4. E is proportional to U, and we have already proven here U is proportional to T to the power 4. That means it becomes E equals to sigma T to the power 4, right? This is our final expression. Now let us go to our next topic, that is giving distribution of energy in black body spectrum. On the image you can see this is showing the distribution of energy in black body spectrum. It is given as wavelength here, and it is power radiated at each wavelength. So that can be considered as the intensity, right? Here is the spectrum for UV and visible. You can consider this is UV range, this is visible range, and the other one is infrared range, right? Now we will see what are the conclusions from these curves. You can see these are at different temperatures. It is given at 1250 Kelvin. Now we are increasing the temperature 1500 Kelvin, 1750 Kelvin, and finally 2000 Kelvin. You can see with increase in temperature, the area under the curve is getting increased. So such kind of conclusions we will see point by point, right? The first conclusion is, you can see the energy distribution is not uniform. With increase in wavelength, or if we consider only one curve at a given temperature, either this, or this, or this, right? at a given temperature, the energy is not uniformly distributed in the radiation spectrum of a black body. This is the first conclusion. Now, second is at a given temperature, the intensity of heat radiation increase first up to a particular wavelength, and finally, after reaching to its maximum value, it starts decreasing with increasing the wavelength further, right? And that wavelength is can be considered as lambda m, where the intensity is maximum, right? Now the third one is an increase in temperature from here to here. You can see 1250 to 2000 Kelvin. What happened? That peak temperature, the peak wavelength that was represented by lambda m, this lambda m is shifted to the lower wavelength side, right? And that gives a relationship that lambda m into T equals to constant. That means the temperature is increasing and lambda m is decreasing to make lambda m into T equals to constant. And this is known as Wien's displacement law. We will see this law in detail afterwards. Okay, now the next conclusion is an increase in temperature causes an increase in energy emission. Energy is directly given by the area under these curves, right? That is the total energy which is emitted by body at a temperature, at a given temperature. So if we consider here, you can see with the increase in temperature, the area of these curves are getting increases. It is found that this area is directly proportional to the fourth power of temperature, and that can be written as E is proportional to T to the power 4, and that is, we have already seen, this is given by Stefan-Boltzmann law. So that is following Stefan-Boltzmann law, right? This is about distribution of energy in black body spectrum. Now we will see the different laws. First law is Wien's displacement law. Wien has shown that the product of wavelength corresponding to maximum energy, that was here, this is the maximum energy. Here you can see on y-axis the energy is given, so the maximum energy is at this point, and that was represented as lambda m in terms of wavelength, and that lambda m was decreased with increasing in temperature. So that was given as here the what Wien has told, that the product of wavelength corresponding to maximum energy lambda m and the absolute temperature T is constant. That can be written in mathematical form as lambda m into T equals to constant, and there Wien has calculated the value of this constant, and it is found as 2.9 into 10 to the power minus 3 meter Kelvin, and this constant was termed as Wien's constant, right? The other thing Wien has shown, that the energy E maximum, that E maximum at lambda m wavelength is directly proportional to the fifth power of the absolute temperature. That means Em is proportional to T to the power 5, or we can write as a proportionality constant, Em equals to constant into T to the power 5. This is our equation number 2. Now if we combine equation 1 and equation 2, we will get E lambda equals to C into lambda to the power minus 5 into F lambda T, that is function of multiplication of lambda or T, where E lambda is the emissive power of the black body, which has the maximum value at absolute temperature T, and here C is the constant, and this F lambda T is a function of lambda T. Okay, now if we want to determine this F lambda T, Wien has done some procedure for this. Wien has some arbitrary experiment, but that was reasonable, and they assume some assumptions concerning the actual mechanism of emission and absorption of radiation. And they concluded, Wien has concluded, that the function should be in the form of A into e to the power minus a upon lambda t, where a and small a are both constants. So if we put this value in our equation 3, what it is becoming, E lambda equals to C into lambda to the power minus 5 into A e to the power minus a upon lambda t. If we combine this A and C, both are constant, we are employing new constant as capital K. E lambda equals to K into lambda to the power minus 5 into e to the power minus a upon lambda t, where K is another constant, and the value of this K is given by 4.94 into 10 to the power 15 in CGS unit, and the other constant, which is given by small a, that has value of 1.43 centimeter degree. This is the formula for energy. Now, if we multiply both sides by d lambda, we get E lambda into d lambda equals to K into lambda to the power minus 5 into e to the power minus a upon lambda t into d lambda. Here E lambda d lambda represents the total amount of energy dE, which is associated with the spectral region lying in the range of lambda and lambda plus d lambda. So that means the range is d lambda. So we have defined a wavelength range between lambda and lambda plus d lambda, and that is the energy which is given by this formula. We can replace this E lambda d lambda by dE equals to, it becomes K into lambda to the power minus 5 into e to the power minus a upon lambda t into d lambda. This expression is known as Wien's law of energy distribution. So we have to remember that we has given two formulas, two laws. One is Wien's displacement law, that is given by lambda m into t equals to constant, and second, he has given the law of energy distribution in black body radiation, that is known as Wien's law of energy distribution, and that is given by d equals to k into lambda to the power minus 5 e to the power minus a upon lambda t into d lambda. However, as I told you earlier, all the classical theories and the laws based on this are failed. They could not completely express, they could not completely explain the black body radiation spectrum. So what is the drawback of this Wien's displacement law? It is not found in accordance with the experimental curves at larger wavelengths. This law was valid only for the reason of shorter wavelengths at lower temperature. If you go at high temperature or higher wavelengths, it does not hold true anymore. Okay, that was the limitation of Wien's displacement law. Now, second, after the failure of this Wien's law, there are other efforts also carried out by different scientists, and one very popular theory, one very popular law was considered given by Rayleigh and Jeans. There are two scientists, Lord Rayleigh and Sir J. Jeans. They have tried to establish a relationship to identify, to explain the distribution of energy with the wavelengths that could be made to fit with the experimental curves. I mean, they have defined their law so that it can justify, it can explain the whole spectrum. According to this law, the energy distribution is given by the formula E lambda into d lambda equals to 8 pi kt upon lambda to the power 4 into d lambda, where k is Boltzmann constant. The other factors you know, T is the absolute temperature, lambda is wavelength, and d lambda is the wavelength region of d lambda. So this equation also actually agrees with experimental results. Okay, but there is a limitation. This was good for longer wavelengths. Okay, or we can say this is valid for lower frequencies. But when it comes to shorter wavelength, this law is again failed. Okay, similar to Wien's law. Wien's law was failed for longer wavelengths, and Rayleigh Jeans law is filled for shorter wavelengths. So actually, these two laws can define one part and another part of the black body spectrum. Right? It predicts this Rayleigh Jeans law predicts an energy output that diverges towards infinity as wavelengths grow smaller, which is not true. You can see here, if we consider this curve, this was the actual curve, the blue one, right? But if we consider this, by putting the value lambda shorter, 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 what will happen? The energy should be increased continuously, and we should get the curve something like this. So this curve is in good agreement up to this range, but after a particular wavelength, it becomes very straight line, almost infinitely increasing value, right? And that is known as UV catastrophe theory. This failure has become known as ultraviolet catastrophe. Okay, this theory is very famous and gives a big failure to the classical theory for explaining black body spectrum. Right, and that's why our next topic is focusing on why the classical theory is failed. So the failure of Jeans law and Rayleigh Jeans law resulting in a discrepancy, right? Because they could not explain the whole black body spectrum, and that generated a ultraviolet catastrophe, a very well-known phenomena, and that suggested a fatal failure of classical physics. This failure of classical physics forced the other scientists to think about new theories, new postulates, new discoveries. And among all these scientists, Planck has discovered that radiation is emitted in the form of quanta, which has energy as h nu. This is a new theory which was given by Planck. In 1900, using this quantum theory, in 1900, he came up with a formula for spectral energy density of black body radiation, which was given as E nu d nu equals to 8 pi h upon c cube into nu cube d nu upon e to the power h nu upon kt minus 1. This is in terms of frequency, where we use nu. Okay, it was totally empirical formula based on the experimental results, and it was given to explain the experimentally observed distribution of energy in the black body spectrum. It was based on his well-known quantum theory of heat radiation, and according to this theory, the energy distribution can be given in terms of wavelength also, which can be written as E lambda d lambda equals to 8 pi hc upon lambda to the power 5 into e to the power hc upon lambda kt minus 1 into d lambda. And when we employ this relation towards the black body radiation spectrum, it fits very well with the experimental results, and that's why this theory could explain, the quantum theory could explain this spectrum very nicely. The ever mentioned theory, this theory was based on some postulates which are known as Planck's quantum postulate, and what was given in these postulates, this can be given in 2 points. The first point is the any black body radiation chamber is filled up not only with the radiation, but it can be considered as filled by the simple harmonic oscillators or resonators, which are actually energy emitters, which can emit energy of molecular dimensions. They are very small, very tiny, and these were termed as Planck's oscillator or Planck's resonators, because he has given this theory. So these oscillators or resonators or tiny particles, tiny molecules, they have similar dimensions as that of molecules. That's why they were termed as Planck's oscillator or Planck's resonators. And they are free to vibrate with all the possible frequencies. Okay, the vibrations of these resonators enters 1 degree of freedom only, right? The second point is The oscillator or resonator or energy emitters, they cannot radiate or absorb any energy continuously. The energy distribution is not continuous. The energy can be emitted or absorbed in the form of energy packets, or these are known as quanta, or they are known as photons. These were postulated by Planck. Planck assumed that each photon or each packet of this energy has an energy equivalent to h nu, where h is Planck's constant and nu is the frequency of radiation. The value of Planck constant is given by 6.624 into 10 to the power minus 34 joule second. Okay, this assumption was the most revolutionary in character for today's quantum mechanics. If there was a particular quantum theory which is based on this postulate, or in other words, we can say that this theory states that the exchange of energy between radiation and matter cannot take place continuously. Okay, so the energy transfer between the matter and radiation, it cannot take place continuously. It happened only in certain multiples of the fundamental frequency of resonators or energy emitters. The energy of photon is equals to 0, h nu, 2 h nu, 3 h nu, or this should be in multiples of a small unit that are known as quantum. So this is all about the Planck's quantum postulates. Okay. Now this is all about the Blackbody spectrum and the classical theories which has tried to explain this Blackbody spectrum carefully. However, these classical theories, the classical laws could not explain it. They could explain only part of it, right? Wien's law was valid for shorter wavelength. However, Rayleigh Jeans law was valid for higher wavelength, but they could not explain together for the whole Blackbody spectrum. But after that, after the failure, Planck has given his theory, and it could successfully explain whole spectrum, right? So now we will see what we have learned from today's lecture. We will solve some questions in today's quiz. Let's start this quiz. The first question of this quiz is given: Rayleigh Jeans law of radiation. The first option is applies to a smaller wavelength. The second option is applies to longer wavelength. The third option is applies to all wavelengths or does not apply to any wavelength. What is the right answer? As we discussed, that Rayleigh Jeans law is valid for only longer wavelengths. At shorter wavelengths, it gives a ultraviolet catastrophic phenomena. Okay, so the right answer for this question, option B, applies to longer wavelength. The second question is: a perfect black body is that which is totally black in color. Second, absorbs all the radiations incident on it. The third option is made of ideal gas, names Krishnika. And the last option is can radiate all its energy. So which one is the right answer? We have defined perfect black body which can absorb all the radiation which is incident on it. So the right answer is option B. Okay, absorbs all the radiation incident on it. The third question is related to Stefan-Boltzmann's law. So according to Stefan-Boltzmann's law, E is equals to sigma T naught to the power 4, E equals to sigma T square, E equals to sigma T square minus T naught square, or E equals to sigma into T to the power 4 minus T naught to the power 4. So the right answer for this option B, we have seen Stefan-Boltzmann's law gives, if we are considering the perverse theory of heat exchange, then this is the right answer. Or you can be confused with this answer. It is sigma into T naught to the power 4, and T naught was the temperature of surrounding black body, not the actual black body, right? So the right answer among these should be this one. The next question is electromagnetic radiation is emitted by all bodies at all temperatures, all bodies at 100 degrees centigrade, all bodies at absolute zero, or only a few bodies at all temperatures. Which is the right answer? Electromagnetic radiation can be emitted all bodies at all temperatures. So the right answer is option A for this question. The next is for a perfect black body, the absorptive power is 0, 0.5, 1 or infinite. Yes, from the definition of perfect black body and the definition of absorptive power, we know that perfect black body is that which can absorb all the radiations incident on it. That's why the answer is 1. So the right answer is option C for this question. The next question is Wien's displacement law is expressed by the equation lambda m into t equals to constant, lambda m t square equals to constant, and lambda m into t to the power 3 equals to constant, or lambda m into t to the power half equals to constant. So we have seen this Wien's displacement law is given by lambda m into t equals to constant. So the right answer for this question is option A. The next question is the absolute temperature of a perfect black body is increased to twice its value. The rate of emission of energy per unit area will be 2 times, 4 times, 8 times or 16 times. What will be the rate of emission of energy? And so first we have to identify which law will be used in this question. You can see the absolute temperature is given of a perfect black body, and we are asked to solve the rate of emission of energy per unit area. This is the relation which is given by Stefan-Boltzmann's law, and that is E is proportional to T to the power 4. So if the temperature is twice, that means 2 into T, and if we make it the power of 4, it will become 2 to the power 4 equals to 16 times. So that means the rate of emission of energy per unit area will be 16 times. The right answer for this question should be D. Option D is the right answer. The next question is the wavelength of thermal radiation is 1000 to 2000 angstrom, 4000 to 8000 angstrom, 2000 to 4000 angstrom, or option D 1000 to 9000 angstrom. Yes, I have discussed this thermal radiation spectrum in electromagnetic spectrum, and we have seen this thermal radiation covers the part of ultraviolet region, some part of ultraviolet region, the visible spectrum, and finally the infrared spectrum. So the total covered area was in the range of 4000 to 8000 angstrom. So the right answer for this question is option B. This is right answer for the question. The next question is related to Planck's quantum theory, Planck's quantum postulates, and it is asking the energy of photon is given by h nu, 2h nu, 3h nu, or 4h nu. So the bundle of energy, or we call it quanta, or we call it photon, has energy equals to h into nu. H is Planck's constant and nu is the frequency. So the right answer is option A for this question. The next question is every body emits radiations continuously to its surroundings, and at the same time it receives radiation from its surroundings. This statement is given by Planck's law, Stephen's law, Provost's theory, or Kirchhoff's law. So if you recall our study, you will find that the heat exchange theory or radiation exchange theory was given by Prof. So the right answer for this question is option C. Provost's theory says that all the bodies emit radiation continuously to its surrounding, and at the same time it receives radiation from its surroundings also. So the right answer is option C for this question. Okay, so that's all for today's lecture. I hope you have learned everything what we have discussed today. It started from, if we recall quickly, the first law we have introduced is Stefan-Boltzmann's law, and we have shown that E is directly proportional to t to the power 4, and then we have discussed that it can be extended for the according to Parvos theory of heat exchange, and it was written as E equals to sigma into t to the power 4 minus t naught to the power 4. Then we have seen after Stefan-Boltzmann's law, we have seen that the black body spectrum, the energy distribution of energy in black body spectrum, and we have seen the curve nature. We have learned about several conclusions from this curve, and after this, we have learned about several classical laws given by Wien's. The first law was Wien's displacement law, that was lambda m into t equals to constant, and the second law was given by Rayleigh and Jeans, that worked at higher wavelengths, okay, larger wavelengths. So these are all classical laws, and finally we have seen why they have failed to explain the total energy spectrum, and according to that some new efforts has taken place, and the important key research was done by Planck's quantum theory, which has given that energy distribution is not continuous. The energy is transferred in the form of packet of energy, bundle of energy, and the smallest unit is known as quanta, or we can call it photon, which has an energy of h nu. So that's all we have learned today. If still you have some doubts, or if you have something to ask, you can write in the comment box. You can send an email to me personally. And for the details on other basic theories, basic definitions, you can consult with the other lectures prepared by me, given by me on the YouTube channel of Suresh Gyan Bihar University School of Applied Sciences. Okay, thank you for your attention. Thank you for listening. Thank you so much.